Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all to the lecture number 13 on the subject of computer organization and assembly language programming. The title of today's session is Design of Counters. Well, dear students, in lecture number 11 we designed the registers for the hack computer. And today we intend designing a special CPU register called program counter. We will start with the overview of the components of the hack computer. Then we will have the overview of counters and their requirement in our computer system. And after setting the stage right, we will design and implement the program counter register for our hack computer. Finally, we will see its demo on the hardware simulator. So let's start playing. Well, this slide shows the bigger picture of the computer system that we intend designing in this part of the course. We have already designed the memory chip, the ALU chip, and different general purpose registers. And today we will design and implement a special type of register that every CPU has, normally called the program counter. So before we start our discussion on the program counter register, let us have a quick overview of counters. Dear students, a counter is a special type of register that goes through a predetermined sequence of states upon the application of input pulses. And the counters are used for normally counting the number of occurrences of an event, keeping time or calculating amount of time between events, and for baud rate generation. Well, baud is actually a unit of speed of transmission, or you can say that baud rate indicates the number of electrical oscillations per second that occurs within a data transmission. In simple words, higher the baud rate, more number of bits per second are transferred. Well, a W-bit counter, by a W-bit I mean 16-bit or 32-bit or 64-bit. So a W-bit counter consists of two main elements. The first is a W-bit register to store the W-bit value, and then a combinational logic that is used to compute the next value according to a specific counting function. Maybe it is a counter that counts simple in incrementing order. Maybe it is a counter that counts in decrementing order. Maybe it is a counter that counts just the maybe even numbers or odd numbers. The second logic that is required with this register is a load capacity. Load capacity means load a new value of user or programmer choice. And finally, it should also be able to reset the counter to some default value, which is normally 0. Well, there are different examples of counters. For example, simple up and down binary counter. For example, a 4-bit up binary counter can count from 0 to 15 and then may repeat. Similarly, a 4-bit down binary counter can count from 15 to 0. We have BCD counter. A BCD counter is a counter that is also called a decade counter. It is normally a 4-bit counter, since it counts from 0 to 9 only. And in case if you want to count in decimal from 0 to 99, you can always use 2 decade counters. And if you want to count from 0 to, let's suppose, 999, you can use 3 decade counters. So BCD counters can be connected in cascade to build bigger counters. Well, you might have studied this gray code in your logic design course as well. This gray code is actually a non-weighted code, also called the reflected binary code, named after Frank Gray. In this code, two successive binary values differ in only one binary digit. For example, a 3-bit gray code counter will count in the sequence of 0, 1, 3, 2, 6, 7, 5, and 4. There are a lot of applications of this gray code, and the one that you all have used is in the Karnaugh map, used for simplification of Boolean functions. Another example of a counter is a ring counter. Well, ring counter is a modified form of a shift register, and a shift register is actually a register capable of shifting its binary information to either left or maybe to the right or maybe in both the directions. Anyways, a ring counter is actually a shift register in which the output of the last flip-flop is connected to the data input of the first flip-flop. And a similar counter to the ring counter is the Johnson counter, and a Johnson counter is actually the reverse of the ring counter, in which the output of the last flip-flop is fed inversely to the data input of the first flip-flop. I hope that in the digital design course all these counters have been taught to you. I've just touched upon these counters that if you want to design them and implement, you can always do that. Anyway, so dear students, the $100 question now is that why on God's earth do we need a counter chip for our hack CPU? Consider a counter chip designed to contain the address of the instruction that the computer should fetch and execute next. In most cases, the counter has to simply increment itself by 1 in each clock cycle, thus causing the computer to fetch the next instruction in the program. In other cases, we may want the program to jump to an instruction at memory address, let's suppose n. So the programmer wants to set the counter to a value of n rather than its default counting behavior with n plus 1, n plus 2, and so on. Finally, the program's execution can be restarted anytime by resetting the counter to 0, assuming that the address of the program's program's first instruction. So if I sum up this slide, so what we need is we need a loadable and resettable counter. By loadable, I mean a counter that can be loaded with a specific value. By resettable, I mean it is resettable to a specific value which is normally 0, and it has an incremented behavior by default. So every computer has a special register called the program counter, normally called the PC, which keeps track of the instruction to be fetched and executed next. And this PC is designed to support 3 possible control operations. The first is reset, that is fetch the first instruction, that is we want the PC to contain 0. The other one is next. By next I mean fetch the next instruction, and we assume that the next instruction is on the next address, so we want this to have a capability of performing a increment operation. And the third one is go to, that is fetch the instruction at address n, which is required in cases of the selection structure, if else and loops, that is we want to place a specific address inside the PC. And this is the abstraction that is shown to you right now. So this is a program counter register having a 16-bit input and a 16-bit output. Remember, since our hack computer is of 16-bit, so we are designing the program counter of 16-bit. For a bigger computer, you can always design a program counter for 32-bit and 64-bit as well. So other than this 16-bit input, it has 3 single-bit inputs as well. The load input, that is used to load a new value inside this register. The increment input, that is used to increment the existing value of this register by 1. And the reset input. And if this reset bit is 1, that means we want to set this PC with a value of 0. So it is also shown over here. If reset at time t is 1, if this reset is 1, then in the next timing cycle we will get a 0 over here. In the same timing cycle we will have a 0 over here, and the next timing cycle we will have a 0 over here. And if the load bit is 1 at time t, in the same cycle we will have a new value loaded inside this PC, the value over here in. And in the next cycle, out t plus 1, this new value will also be available on this output out. And if the increment at time t is 1, if this bit is 1, the value inside this program counter is incremented by 1 in the same cycle, and that new incremented value will be available on this out in the next timing cycle, as shown over here. And if all of these are false, then do nothing. No content change will occur inside this program counter. So if you have a clear idea of this counter, just at a very abstract level, let me show you a simulation to have a more clear understanding as how it behaves. So this is the timing diagram. You can see the clock that is ticking in this direction. These are the discrete cycles, cycle 22, 23, 24, 25 and so on. These are the in values that are 16-bit in values that are available over here. So at cycle 22, at the in we have 5 to 7, and at cycle 30 at the in we have 5 to 7 again. This is the increment, this input, and over here it is 0, and over here it is 1, and then again over here it is 0. This is the load input, which is 0 for all these cycles, and over here it is 1, and then again it is 0. This is the reset input, 0, then 1, then again 0 and so on. And this is the value at out. So let me show you one by one. Let's suppose that right now it is a cycle 23. At the in we have 5 to 7, that is over here we have 5 to 7. The increment bit is off, so no increment. Load is 0, so no loading. Reset is 1. So if the reset is 1, that means the contents of this register will be reset to 0. And at the next cycle, that is cycle number 24, we will have a 0 at this out. Okay. So at cycle 24, the increment is again 0, the load is 0, the reset is 0. All these three inputs are 0, so no change in the contents of the program counter. So at cycle 25, we have the same value. At cycle 25, the increment has been raised to 1. The load and reset are 0. So increment is 1. So if the increment is 1, that means the contents of this register will be incremented, and that incremented value will be available on out in the next cycle, that is 1. So you see at cycle 26 you have a 1 over here, and since over here as well the reset is 0, load is 0 and the increment is 1, so it will be 2 over here and 3 over here and 4 over here. So let's understand this cycle 29 now. Excuse me. So at cycle 29 we have the increment as 1, we have the load as 1 and the reset as 0. So since the load value is 1, so this 5 to 7 over here will be loaded in this register and will be available on out in the next cycle. So you see we have a 5 to 7 over here, and since in cycle 30 we have the increment on 1 and load and reset are 0. So this is just incremented to 5 to 8 and 5 to 9 and 530. So at cycle 33 you see now the increment value has gone to 0, the load is 0 and the reset is 0. So that means the increment, load and reset, all these three are 0. So no change will occur in the contents of this counter. So at cycle 34 we should have the same value 530, and this process of course goes on. So dear students, I think now we have a very fair idea on the working and the behavior of this special register called the program counter. Let us try to implement it now. Well, dear students, to write the HDL for a 16-bit program counter, the basic building block that we need is the register chip. Since you see this is basically a register. And this is the HDL of the register chip that we designed in the previous lecture, I think. And from the interface of this chip, it is clear that it has the two inputs, a 16-bit in and a single bit load, and a 16-bit output named out. Well, this register is using 16-bit chips, and the HDL for the bit chip is also shown over here. I will not go in the details. We have spent a complete session on these two chips. I think that was lecture number 11, and other than this, in the block diagram over here, this PC register has another input, the increment input INC, and if this is set, the contents of the program counter will be incremented by 1, and this functionality can be achieved by the increment 16 chip, INC 16 chip that we designed in, I think, lecture number 8. And here is the HDL code of that chip. So this chip has a 16-bit in and a 16-bit out. The implementation part of this chip shows that it uses another chip, add 16, that simply adds a 1 in a 16-bit number and place it on out. Moreover, dear students, we also designed this add 16 chip as well in the same lecture, I think, and the HDL code for this add 16 chip is also shown over here for your understanding. And this add 16 chip actually adds two 16-bit numbers and generates a 16-bit output. The implementation part of this add 16 chip shows that it uses a half adder chip to add the two least significant bits of these two numbers A and B, and 15 full adder chips to sum up the remaining 15 bits of the two input numbers. And of course, we also have designed this half adder and full adder using the gates. Anyway, I think now we are ready to write down or understand the HDL for this 16-bit program counter register. Let me move on to the next slide. And dear students, for your ease and comfort, here is the HDL implementation of this PC chip as well. The name of this chip is PC. The interface tells us that there is a 16-bit input named in, a single bit input named load, a single bit input named increment, and a single bit input named reset. And finally there is a 16-bit output named out. And this is what the interface is also shown over here in the block diagram. Let's see the chip implementation part as well. This increment 16 chip or INC 16 chip inputs the existing register contents and outputs an incremented value. Then we have a MUX 16 chip whose code is also shown over here. We designed it when we were designing the combinational circuits, and uh, the behavior of this MUX 16 chip is such that if the increment bit is 1, then this MUX 16 output this incremented value on the output, and if this increment bit, which is over here on the selection of this multiplexer, is 0, then no increment is done and the existing register contents are placed onto this out. This second MUX 16 decides whether to load a new value in the register or not, depending um, on the value of its selection input load. So if this is 1, the new value that is there on the in will be placed over here, and if this is 0, the value which was here will be placed on out. The third multiplexer chip, this one, decides whether to reset the value of the register to 0 or not, depending on this selection input, that is the reset. And finally, if all of the above conditions are false, or let me rephrase that, if the load and the increment and the reset inputs are all 0, then the same register contents are again loaded inside the register. Well, dear students, if you still have a doubt in its behavior or code, please listen and view this part of the video again. And now it is time to have a demo of the working of this chip on the hardware simulator. And let me move on to the terminal. The hardware simulator is already running. Let me load the chip by clicking this button. And I know that inside the lecture codes and 13, and this is the pc.htl chip, and here is the chip, and you can see the code of the chip over here, which we have just discussed on the slides. If you see the input pane, we have the in 16-bit input, the load, increment and the reset input, and here we have the out 16. So let me just keep a 0 over here and set the increment to 1, and let me run the clock. Tick tock, tick tock, tick tock. So you see the value is being incremented. With every tick the value is incremented, and with every tock the value is placed on out. If I want to load a new value in this register, I place let's suppose a new value over here, 127. I set this increment to 0 and I place a new value over here. So this is the load input is 1, the in contains 127. I do a tick and I do a tock. So you see a 127 over here. And now if again I want to come in the increment mode, I just do something like this: tick tock, tick tock, tick tock. And if I want to reset, I just need to reset this one. And once I reset, irrespective whether what is the load or the increment value, this value will be reset. So tick tock. So dear students, I think I have made the concept clear. So please do practice it, and meanwhile let me fall back to the slides. Okay, so dear students, that is all for today's session. I want you to perform the testing of this chip on the hardware simulator. If you don't want to write the code, you can always download the code of this chip from the class PUCIT repository. Interested students should also try to design, implement and simulate binary up and down counters, cascaded BCD counters, gray counter, ring counter, and Johnson counter. And this will make their concept very clear as far as the concept of or the term of counter is concerned. But anyways, that is all for today's session. I hope the session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.